So before we start, so you all have taken your first quiz. I hope the grader gets it quickly. I will pick on the grader about that. But give us a little while to kind of get adjusted. Some of you kind of messed up the thing. So anybody that missed the quiz because they messed up, and I heard emails from all of you that had problems, here's the deal I want to make you, right? You don't get to make up the quiz, but if you don't miss any other quizzes, I will replace your missing quiz with the average of the rest of your quizzes, so it doesn't hurt you at all. Okay, so if you're in trouble and can't figure out how to do this, let me know. But everybody should make a single PDF file and upload it. Even if it's multiple pictures, you can make a single PDF. If you have technological problems with that, then come see me so I can screw you up further. Okay, any questions? All right. So what we were talking about last time is I introduced this kind of matrix multiplication, right? So suppose I have this is a suppose this is an m by n matrix. And what I mean by this notation is this is the first column, this is the second column, and this is the n column. Everybody okay with that? And hence the n columns in the matrix. And when we multiply this, and I told you all how to multiply matrices yesterday. If I look at, suppose I have x, by the way, this is an m by n matrix. And I want to multiply it by a vector. How tall is my vector? Must it be for me to be able to multiply it? Which?
No, and.
Right, because remember how we've got a match here, right? So n x must be an n row and one column matrix. You got to have that matching to make this work. Then, if you multiply this out, ax and I encourage you to do this with small matrices so you can see how this works out. But there's a nice formula for it. This is actually you actually get this vector here. It's x1 times the first column, x2 times the second column, all the way up to xn times the last column. And of course, these are all n by one column vectors. And so when you add them up, you'll get some nice big n by one column vector. I think I gave you this theorem last time, but I'm going to review it here. Theorem. Here, A is n by n matrix, and by the way, let me ask you this: when I took my n by n matrix and multiplied it by my n by one column vector, you all see that we had to have the same ends, right? Or what's my output? What does it look like?
M by one.
It's m by one. It's got to collapse in the middle, right? And that's why B is in Rm, because I'm going to multiply this by a vector and I'm going to get an output that's an m by one vector. Then the matrix equation AX equals B has same solution as vector equation x1 b1 plus x2 b2 plus xn bn B, which has the same solution as the augmented system of linear equations. This is one we played with before. Uh, so let's so basically what we're doing is we're tying all this together. And this is all kind of from those first linear systems. This is just different ways of seeing it. So let me make the following note. So AX equals B has a solution. That is to say, is consistent, maybe. If and only if B is in the span of the columns. That is to say, B is a linear combination of the columns of the matrix, right? Because that's exactly what this part of the equation says, right? Notice this has the same solution, and this has a solution if this has a solution. And what this means is B here is a linear combination of columns. Okay. Let me give you a theorem here. So as we go on in this class, I'm going to add more and more to this theorem, but when we get to some further sections, I'll add more of this. You'll see this theorem coming up, but here's what we know so far. Let A, B, and R. So of course, remember, this just means that A is a M row by N column matrix. The following are equivalent conditions. Don't let that terminology throw you off. What this means is the statements I'm going to put down are logically equivalent. So if you have one statement, then you have the other statements. So these are basically what this means is these are all saying the same thing. For all B and Rm, for every possible vector B, AX equals B solvable. If no matter what B is, you can solve this equation, then two, it's also true that for all B in Rm, B is a linear combination of the columns of A. So if no matter what B is, you can solve this equation. This means that no matter what B is, it's a linear combination of the columns of A. 3, the span of columns of A. Remember what the span is, that's just all possible linear combinations is all of Rm. That means every possible vector in Rm. And number 4, and this last one is kind of the working mathematician's way of thinking about it. It's kind of convenient when you're doing computations. A has a pivot in every row. Okay. So we give an example. Let A be 3, 1, 7, 2 minus 2. Okay. Does AX equal B have a solution for all B in, by the way, what's my appropriate exponent here? Okay, so what's the size of this matrix? It's 2 by 3. So if I'm going to multiply by vector x, what size does x have to be? If this is a vector, it has to be 3 by 1. Everybody okay with that so far? So, and what's it barfing out? What size is this going to be? 2 by 1. So this should be an R2. Let's attempt to solve this. Does this have a solution for every? And let's solve this as quickly as possible. I would use, let's see, I'm asking about 1 for every, is it solvable for every B? I'm going to use 4 because these are all equivalent. All I need to do is check if it's got a pivot in every row. Well, by the way, does it look like it? It looks to me like it probably does have a pivot in every row. So let's try this. Let's just take the matrix A and let's row reduce it. All right, I'm going to leave this on the bottom. And I'm going to multiply by -3/2 and add it up here. Groovy, right? So this is going to be, well, 0, and that's the point. Times -3/2 is going to be 3, and 1 is 4. -3/2 is minus 15/2 plus 14/2. Tell me when I can be done. I'm a situation now, right? So let me do it. Maybe clear this out. Let me multiply this by 1/2 and put it on top, right? 1 minus 1, 5/2. And let me multiply this by 1/4 and put it on the bottom. It's not row reduced echelon form, but is it clear to you all that there's a pivot in every row? Okay, so this is always solid. Right, okay. So that's kind of cool. By the way, with the experience of that example in hand, let me ask you this. let's go. Um, um, is AX equal B solvable for all see, this is a 3 by, I'm sorry, this is 4 by 3 matrix. So again, I'd have to multiply by a 3 by 1 vector and I'll get a 4 by 1. Is this solvable for all these? I'm not even going to do this. Can you tell me by looking at, tell me why you know? Yes.
There can't be a pivot in every row.
There can't possibly be a pivot in every row, right? Because every pivot corresponds to a different column, right? How many columns you got? 3, right? How many rows I got? 4. I can't possibly get a pivot in every row, right? So no way. That's kind of a nice spin-off of this, right? Because what I see from this is if I have more rows and columns, I'm in trouble as far as this theorem goes, right? Everybody okay? Okay. Now, any questions? All right, so I'm gonna move on to section 5 here. We're going to talk about homogeneous equations here. We've been looking at, and I did a couple of examples of we call this a matrix equation, right? And we saw that this is basically a linear combination of the columns, and we can also think of it as a system equation, whatever. Now, I'm going to take a super special case, and it looks like I'm specializing a lot, but it's important actually to the theory, and it's actually important in building general solutions. What if we consider be as simple as possible? This is called a homogeneous equation. And actually, the solutions to this have a great deal more structure to them. This is a little bit fast to notice. The solutions to the homogeneous equation we're going to see later actually form something called a subspace, and it's actually very important. But here, there's one thing about homogeneous equations that's different than this, that's better. When I have a system of equations or a single equation or whatever, what is one of the first questions that you should ask yourself? If I walk up to you on the street and say, solve this, what's the first concern you might have? That's right. I'm, evil Professor Jim who gave you something that is unsolvable. So you sit there with the pulling of the hair and the gnashing of the teeth, right? That's all. So there's always a concern, we've seen this, that you have a system that's inconsistent. Oh, there's no solution to this at all. Homogeneous does not have this problem. Can you tell me why? What's one solution? What's one value of X that's going to work for sure? The 0 vector always works. The homogeneous always has solution X equals the 0 vector, whatever the appropriate size of the 0 vector is. Right here it would be 3 by 1. So, for example, if I have the matrix 2, 1, 3, minus 7, 1, 5, this is my A, say, and my output should be 0, 0. Notice if I plug in 0, 0, 0 here, and you multiply this out, it's gonna work, right? And this also, so just like you have homogeneous equations written in matrix form, I can write this as a system, a homogeneous system. So in this case, it would be 2x plus y plus 3z is equal to 0, and minus 7x plus y plus 5z is equal to 0. This is a homogeneous system. From linear equations. And is it pretty obvious to you all that if you let x and y and z all be 0, that it balances both those equations, right? Homogeneous is cool because you've always got the trivial, the 0 solution, for sure. And of course, the big, and of course, what is also true is these are also linear equations. So what's the big question for homogeneous systems or a homogeneous matrix equation? You know you've got the one solution, so you're never going to be inconsistent. Your only question is, do you have one or do you have infinitely many? Right. And we've actually done this a little bit, but I don't think that practice is going to hurt anything. Let's look. Let me make this following observation here. Before we get down to doing some computational stuff, let me give you a couple of remarks that we've been kind of using, but I think I should put down for your notes a bit. There. Suppose that A again, suppose we've got your favorite m by n matrix. Let's say that U and V are n, which just means, basically, it just means you can multiply A by U, right, and A by V, because this is n by n, this is n by 1, so, and your output is going to be n by 1, right, okay. And let's see, and lambda is in R. This is just a number. That's it, just a number. Number one, when you multiply A times U plus V, what do you get? Oh, well, theorem I'm writing down. What do you hope you get? How do you hope you can rewrite this? Yeah.
AU plus AB.
I hope so. And indeed, our wishes come true. So multiply these things out the way you think. Again, these are all easy proofs. All you have to do is just write things down. You want to prove it, come to my office and have to do it, but it's kind of a yarn. And okay, so A times U is just this matrix, m by n times this n by 1 vector. What happens if I multiply that by a number? What do you suppose happens?
Well, you're just multiplying the vector by a number, so it still lets you get a vector output.
Okay, right. Yeah, so you can multiply AU first and multiply lambda times the end result. You can do this any way you want. You can't pull vectors out, but you can pull numbers out of this. So what is the significance of this? Well, we're going to again get into this deeper a little bit later. But here, let U and D be solutions to homogeneous equation. AX and I know. Then this is very interesting, because if you have two solutions to a homogeneous equation and you add them up, there's still a solution. Right? This is actually really this is one of the reasons that this linear algebra is so important. In general, you don't expect solutions of equations, even linear ones, to add up and still be a solution, right? Example. This is certainly not a linear equation, right? Everybody see what the solutions to this one? Right, I mean, this factor, this is like x minus 1, x minus 2. Right, so the solution to this are x equals 1 and 2. And you can plug it in and see. Right? What happens if you take two solutions and add them up?
It's not a solution.
It's not necessarily a solution, right? 1 plus 2 doesn't work. What happens if you take a solution, multiply it by a number? It's not necessarily a solution. This is actually kind of a fantastic theorem. This works. How many of you said that you took 2080? Right? In 2080, you probably saw something like, oh, you've got these homogeneous equations. If this is a solution, that's a solution, and the sun's a solution, right? That's a big important part of this right here. One of the nice applications. And actually, I'm going to prove this because even my single size brain is right. Look at number 1. What does it mean to be for these to be solutions? We know that AU equals 0 and AB equals 0. Right? That's what it means for these two animals to be solutions. Right? So this means that AU plus AB is 0 plus 0. Right? And I don't know much, but I know that if I add the 0 vector to itself, I get the 0 vector. Agree? And I know from this over here that I can pull that A out. U plus V also is a solution to that equation. Right? It's very, very important that these are homogeneous here. Even if you have non-homogeneous, even linear systems doesn't work. And if AU is a 0 vector, well, if I multiply any number, it becomes a 0 vector. It's still a 0 vector. Right? And by part 2 over there in this theorem, this is A comes land to U. And there you go. So both numerical scalar multiples of solutions are solutions and sums of solutions are solutions. That's kind of cool. But, yes, sir.
Not directly, but if you solve a bunch of homogeneous equations with a augmented matrix, wouldn't the right side always be 0, no matter what you do? the row operations, or is there something that will?
The right side, what you're doing is when you do the augmented matrix, what happens is you reduce, you know, that little dotted line on the draw, right? What you're doing is you're reducing that stuff on the left of that dotted line. And if you're not homogeneous, then it's possible that you've got numbers that are not zero. Right.
So for homogeneous, you don't care about the right.
Oh, okay, right. So if it's homogeneous, that's an easy, we're gonna do one of those,
Okay.
but it's easy because they're all zeros, so every row operation you do just leaves everything zero. That is
Yeah.
super sexy, because you never have to do anything till the step is to the right of the little dividing line, right? So, let me make an observation, that we'll see in practice, here. So. So theorem, and I will prove this one, which might, mess around with this is kind of fun. A homogeneous equation. AX equals 0 always has X equals 0 as a solution. And what is more, X equals 0 has a non-trivial solution. What do I mean by non-trivial? Sometimes people call the zero solution the homogeneous trivial because it's always there. This has so what I mean by this is AX equals 0 has a solution other than the zero vector. If and only if the matrix A, after you reduce it, has at least one free variable. So in other words, when you go through your system and reduce it, what will happen is for all your variables, they'll either all turn out to, if they all turn out to be basic variables, right? So if there's a pivot in every row, they all turn out to be basic, or I'm sorry, pivot in every column, then you'll have only have the zero solution. On the other hand, if you have at least one free variable, you'll have infinitely many. So let's look at a couple of examples here. So let's let A be, in this case, 1, 1, 0, 0, 1, 1, 1, 0, 1. And I guess X, well, what X is X1, X2, X3. And for the further details, I'll start shortcutting the details a little bit. And in this case, by the way, what should be the size of my zero vector here? Yeah, it should be. That's exactly what. Right. Yeah, it should be the size of the number of rows of the mission matrix. Another way, so let me write this parenthetically, even though I said in this example, I'm going to, look at this matrix equation. Let me point out the intimate connection with systems. This is equivalent X1 plus X2 0, X2 plus X3 is 0, and X1 plus X3 is 0. It's equivalent to this system. Now, for this example, just kind of so we can see, I am actually going to write my augmented matrix, but in the future with homogeneous systems, sometimes I might omit that last column since it stays all zeros. And you'll see that here. So let's go through, just like it's a system and try to figure out what happens. So let's augment the matrix. 0, 0, 1, 1, 1, 0, 1. And like I said, you got a lot of homogeneous because you've all got zeros down that right-hand stripe. Now, what I'm gonna do is I'm gonna go for it here. I'm gonna multiply this by -1 and add here. So this becomes 1, 1, 0, 0, 0, 1, 1, 0. Comes -1 and add. Comes -1 and add. Comes -1 and add. And -1 times 0, add to 0, 0. So you all start to see why it doesn't matter what row operations I perform over here. I'm always going to get the 0, 0, 0 on the right side. Right? It's always going to be something times a 0 plus another 0. Right? Okay, so let's see where we're at now. I guess what I can do is I can now add. I'll just straight up add, multiply the second row times 1 and add. And 0, 0, 2, 0. Notice I hope it's apparent at this point. How many pivot columns am I going to have? I think actually I'm going to make this one and this one all in. So it looks like there's no free variables. So that means that there should be, if this statement over here is right, that should mean that there's only one solution. Okay, my next move is I'm going to multiply this by 1/2. Is everybody okay with me just kind of replacing that with 1? So I don't have to redraw everything. Let's do that. I'll replace that with 1. Now I'm going to use this bottom row times -1. Take out this. So I'm going to have 0, 0, 1, 0. Times -1 and add 0, 1, 0. And 0, of course. And I guess I don't need to do anything here. And in the last step, I'm actually going to multiply by -1 and add here. And what I'm going to get is 1, 0, 0, 0, 0, 0, 1. That's certainly a reduced echelon form here. And of course, now you can just read these off. And there you're forced. Okay. Let's do another one. Let's do, let's try this one. Again, I'm going to do a 3 by 3. I'm going to go 102, 1, 5.1, and 1, 2, 4. And again, I'm tracking the homogeneous equation. So I'm going to do the same kind of technique, but I'm going to, in this case, I'm going to omit right augmented part. I'm just going to reduce that matrix A using row reduction because I can, if you're not comfortable with it, you can just reduce it and then put that extra column zeros at the end because nothing's going to change about that. So let's just take the matrix here. 1, 0, 2, 1 minus 1, 1, 1, 2, 4. And I'm gonna double reduce. I'm gonna multiply this by minus 1 and times minus 1. Take out the ones here. So I'm gonna get 1, 0, 2. I'm gonna get 0, the minus 1 and add, minus 1, and I am going to get 0, 2, 2. How about 2 minus? Right? Notice these two are essentially the same. Do I agree with that? Because both of us got minus 2 this. So let me do this. I just multiply this by minus 1 and this by half. And now I'm going to use this to take out the bottom row. Okay, a little different here. How many pivot columns do I have?
2.
I've only got 2 in this case, right? And this is in low reduced echelon form, is it not? Right? Well, let's write down the solution because we don't know how to do this. Let's write our simplified equations. So this first one is x1 plus 2x3 is equal to 0. And x1, I'm sorry, x2 plus x3 is 0. And the way I've got this set up, what's my free variable? X3 is my free variable because it's the one that comes out of the non-pivot column, right? Everybody okay with it? So if I've written a linear system, here's my linear system. My basics in terms of 3 and x2. So x3 could be anything you want, 17, 25, -3, whatever. And they control x3's choice controls what x1 and x2 are. Everybody agree with me? But this is a matrix equation. Can I write this as a vector? Anybody see how to write this as a vector solution? Well, here's what I do. I'm going to write this as a vector solution. There it is. Right? I'm being a little facetious. Now I've got extra information. I know x3 is free, so there's nothing I can do about that. x3 is just got to be x3. x3 just being x3, like Danny McBride or something. And x2 is now minus x3. And x1 is minus 2x3. Everybody okay with me? Now notice x3 can be pulled out of this vector. So the vector -2, -1, 1 times this matrix will be 0. And not only that, any freaking multiple of it. Take this vector multiply by 2, take this vector multiply by 7, or whatever. Pick x3 any way you want. So this is kind of another way of writing this. This represents your x1, your x2, x3. Everybody okay? In fact, let me point out follow the theorem, and then we'll at least get a ways into the example of this. Consider matrix equation A. Okay. Let it be vector be any solution to let me see. So let's suppose that you can find some solution, we'll call it, right? Suppose you're just lucky and you can guess and check and you get a solution. So this means that A times P vector is B vector. Am I cool with that? Then any other solution AX equal B is a form plus X sub H, where X sub H is a solution to homogeneous. This is actually a fantastic result, and it tells you a lot about the structural solution. What this means is, when you find any solution to this is in terms of a particular given solution plus a homogeneous, right? And it doesn't matter which solution you get. You can have two different solutions to this, they're both in this form, right? So, for example, where A equals this matrix in the previous example. 1 minus 1, 1, 1, 2, 4. Then any homogeneous is in the form of x3 times minus 2 minus 1. And in fact, let me write x sub h. We found out in the previous example that any solution to that homogeneous equation is that. Everybody? So suppose we have so let's take this matrix here. There's my A. Let's take this, okay, suppose that this is B here. And this is my, anybody see a solution to this? I made this up because I know what the solution I created in my mind. Everybody agree that works? Let's check it, shall we? 102 times this. So first, the first row, first column should be first row times first column. 1 times 1 is 1, 0, 3. Everybody agree with that? Okay, let's see if I got this right. 1 times 1 is 1, 0, 2. Got it. 1 times 1 is 1, 0, 4, 5. Everybody agree with that? This is also the system x1 minus x2 plus x3 is 0, and x1 plus 2x2 plus 4x3 is equal to 5 times 0. What this theorem says is any solution which in our case is 102, 1 minus 1, 1, 1, 2, 4 times x 2, 3, 2, 5 is of the form my known solution plus XH. All solutions, which is in our case 101 plus some number times -2 minus 1. Now, check me on this. This is a good exercise for you to get used to it tonight. Go home and take this system of equations, which we have solved, and solve them just the way we did it, and turn it into a vector form. You might not get something that looks exactly like this, because you might have gotten this one different. This vector right here could be, for example, -1, -1, 2. But you should be able to write any solution you get. And check me on that. Let me know if you get it, and we will see you on Friday. I will probably post it. Your next quiz will be Friday at 5, and I'll probably post it this afternoon. Probably.